So when I've got my motor spinning, the quad is fighting gravity and it is hovering at a position. To go forwards, what you do is you turn the front two motors down and the back two motors up. That causes the quad to pitch forward. And now all of a sudden your thrust vector is at an angle to straight down, so it becomes maybe 45 degrees, in which case your quad is propelled forward. It's the same for going backwards, left and right, you just change the motor speeds. Now, can anyone tell me how a quad yaws or how a quad rotates like this? It's a little bit counterintuitive. Someone who's not the lecturer on quads. How do you guys, like, if you think about it, like to go left, I sort of roll the quad left and then the vector is changed. But how do you reckon I get the quad that's sitting here to rotate left and right? John?
You change the torque because you have the turning torque each motor. So you have two motors, they're turning the opposite direction, your propeller's turning the opposite direction to the other two. Yep. So you change the speed of those and that rotates the frame.
So if you have a look, the rotation of these propellers is not the same direction. They actually alternate. So this one here is a clockwise rotation, this one's counterclockwise, clockwise, counterclockwise. And so what it does is it turns up the alternate motors, and then because of Newton's laws, basically there's more torque from the motor spinning clockwise that causes the multi-rotor to spin clockwise. So that's how it rotates on its yaw axis. So on a quadcopter and other multi-rotors, they're pretty mechanically simple compared to a lot of other flying crafts. Basically you have motors with propellers on them. You have these little electronics here, which are your speed controllers, or ESCs, electronic speed controllers. They're hooked up to a flight controller, which is normally some sort of flight computer doing calculations. You have a receiver that is receiving signals from a transmitter like this, which is how you control it. And that's basically all that you need to fly. Very, very simple. So, first of all, flight controllers. Why do we need them? So a flight computer, like for fixed wing planes, for example, they don't need flight computers to fly. You just have servos that are controlling your flaps and your ailerons and basically all of the different bits on the craft, and they are directly mapped to the stick inputs you have on your thing. And so you push the throttle stick up and it spins the propeller faster, it goes forwards. You want to pitch up and down, you move the flap up and down with your servo. Now on a quad, because there's a lot of complicated stuff happening with the four motors mixing together, you need a flight computer doing calculations. And so this flight computer actually has a bunch of sensors in it. So the basic sensors you have are sort of your accelerometer, which is basically what gives you your absolute rotation. So it knows that it's flat, or it knows that it's at this angle or at this angle. You also have a gyrometer, which is telling it the speed at which it's rotating on an axis. So it gives it a value basically in degrees per second, so it knows that it's rotating this quickly. And then they're the basics. They're the only sensors that you need to actually be able to fly one of these stably in a stable system. There's a bunch of other sensors you can get. So this one only has those two sensors, whereas the DJI Inspire 1, for example, has a bunch of other ones. So you have a barometer, which gets your air pressure, and that allows it to know what altitude it's at so that it can hover at a specific altitude and stay there. And they're pretty accurate. They're not like accurate to the centimeter, but the one in the Inspire 1 I think is accurate to about 20 centimeters. So you can say sit here and it knows by the air pressure that it's at this spot, and if it starts dropping because of battery level or something like that, it detects that change in pressure and then increases the motor speed to compensate for that. There's also a magnetometer, which is a super fancy way of saying a compass, so it just measures magnetic fields so that it knows which way is north, and it knows absolutely which direction it's facing. You then have GPS, which is pretty self-explanatory, so you can see in this craft here there'll be a GPS up in this puck. They basically give it a position. You can also, so the one in the Inspire 1 is nice in that it can hook into both the American GPS system and also the Russian GLONASS system, which are different constellations of GPS satellites, which give you a little bit more precision. GPS basically works, so GPS satellites, for those of you who don't know how they work, they're basically up there in the atmosphere saying, ping, this is the time. Ping, this is the time. And then your quad goes, this satellite is over here, this satellite is over here. This satellite has taken this many seconds, and they're all synced via atomic clocks. And it looks at the difference in time, so the time it takes to go from that satellite to the quad to triangulate a position. So the more satellites it has, the more accurate that position you can get. So for consumer GPSs, you can basically get down to about a meter precision, not much higher than that. Like if you start using some of the more industry level GPSs, you can get them much lower by a lot of fancy stuff. But generally with these, you'll get to about a meter precision if you've got 15 to 20 satellites that you can see in the sky. There's a bunch of other things as well that you can get. So sonar, which is where it emits a noise, listens to how long that noise takes to come back. So that's something that we added to the Inspire 1 and the Phantom 3. So there's actually a sonar sensor here. So there's a speaker and a microphone which basically emits a clicking noise constantly. There's also optical flow, which is what this one here is as well. So for you guys who know what an optical mouse is and how that works, they've got the little camera on the bottom that looks at basically reference points, and then it looks to see where they've moved, and then does an average of that to know which direction it is. So that allows the Inspire 1 and the Phantom 3 to get a position lock and stay exactly where they are indoors when it can't get GPS. So I can hover it right here above and it'll see that the table is there, and it'll know where it is and know to stop because of that optical flow sensor. There's a bunch of other research going into computer vision as well, so actually analysing objects from the feed that you're getting from the camera. That's still sort of more in the research phase rather than the consumer phase. There's a lot of work going into it, but speed-wise it's still a little slow, and the onboard computers aren't fast enough to process it unless you have something like an FPGA or something like that. But mostly those things are sort of more relegated to the research realm at the moment. It's looking like it's going to move towards that. And then there's other systems as well, like LiDAR, like what the cops use for getting how fast you are, where it basically emits light, similar to sonar but with light instead. And so the flight computer can use all of those sensors and it combines them all to give it the best model it can of where the quad is, and you can tell it where you want it to be, and then it uses those sensors to provide the amount of change that it needs to reach that changed state that it needs to be at. I'll be talking a little bit more about the actual different flight computers later on, but that's basically what it is. So what can they do? With a flight computer like the one that's in this quad, this one basically just does what my transmitter tells it to do. I say go up, it goes up. I say go to this angle, it goes to this angle. And it's pretty dumb. Whereas you look at the Inspire 1, or I'm assuming this is running an APM. Pixel, yeah, which is running an APM, which has a lot of autonomous capabilities. So you can do waypoint navigation, you can do spline waypoints where it does circles around things, you can have it survey stuff autonomously, take off and land autonomously, and lots of other things. And so there's a lot of scope between what flight controllers can do, and that sort of comes into the price as well, because the flight controller in there is about $250, whereas sort of your typical flight controller for a racing drone, you're looking at about $30 or $40. And the difference is the sensors that are on there and the software that runs on it. Next, you have motors. So there's lots and lots of different types of motors. You can see these ones are pretty small compared to the ones on the Inspire 1, and they range in size. Now, when you're looking into motors and you're looking at building a multi-rotor, there's a couple of different values that you'll look at. And to begin with, so when you get into this hobby, there are so many numbers that you get overloaded by. I don't understand what this means, and how do I know what this value and this value go together to get the right thrust that I need for this size and that sort of thing. So the main value that you look at when you're looking at motors is your kV rating. kV is not kilovolts, as a lot of people think when they initially get into the hobby. kV stands for basically rotations per minute per volt. So the one thing, the Phantom, this white craft at the front, I'll just use them because they're easy to calculate. They are 1000 kV. So that means that those motors, when they don't have a load on them, they don't have a propeller, they will theoretically spin 1000 RPM per volt. The battery in the Phantom is about 14 volts, which means it'll technically spin 14,000 RPM. And that's the speeds that those propellers will be spinning. Now, when you put propellers on and you put weight on it, that obviously drops, but that's sort of what that value means. So the motors in this mini quad are 2,300 kV, so they spin to 1.5 times more than what the Phantom does. And I'm assuming these little motors here are more like 3,000-ish kV. And then the ones in the Inspire are probably more like your 500, 400 kV, so they're much slower. Now, why would you use slower kV versus higher kV? And why would you just go for the highest kV? Now, the thing is with motors and kV is the lower the kV is, the more torque that motor has, or the more force it has to rotate things. So on quad like the Inspire, where it's got bigger propellers, you want lower kV so it has enough torque to spin the bigger propeller. So these 2,300 kV motors could not spin the 13-inch propellers that are on that. And if I put these little motors here, these little propellers, sorry, the little 5-inch bull nose propellers on the Inspire's 500 kV motors, it would be able to spin them fast enough to get enough thrust. So it's very much a balancing game. Now you get those from, I'll just touch on this very briefly, you have the stator size of the motor. So these motors here are 2204, which basically means 22 millimeters wide and 4 millimeters tall is how big the actual stator is that the motor is, and these ones are more like 14 or something like that. And basically the kV of the motor is determined by the number of windings. So has everybody in here seen the inside of a brushless motor before? Yeah? So you're all pretty familiar with how they work and how the windings work and that sort of thing. So I won't go too much into that. But yeah, so that's basically how the motors work. Now you have your ESCs, which are speed controllers. The basics of these are basically they receive a signal from the flight controller saying spin this quick, and then it spins the motor. Now, if there's anyone here who doesn't understand how the brushless motors work, basically there's 3 phases going into them, or 3 wires, and then there's poles around it with magnets attached to the outside housing. And what it does is it turns those poles on and off in a sequence to cause, which turns them on magnetically, I should say, which causes the motor to rotate through magnetic propulsion. And that's basically what the speed controllers do, is they control the changing of those phases to rotate the motor. And if you want it to go faster, the speed controller spins that faster or slower. It takes the power from the battery to do that. That's the basics of ESCs. The hobby ESCs have actually come a very long way in the stuff they can do, but I'll talk about that in a little bit. Batteries, pretty much all multi-rotors will be using lithium polymers. I'm not really a chemistry person, so I can't tell you the difference between a lithium polymer and nickel metal hydride and all the others. Basically, they have a higher energy density, so you can get enough energy in them based on the weight. Previously, before lithium polymers were cheap and consumer available, you couldn't really have multi-rotors, which they're basically the main reason multi-rotors have exploded in the last 5 or 6 years is because lithium polymer batteries have become cheaper and easier to get. And so we're looking to the future. There's new battery chemistries like lithium sulfur and those sorts of things that give you higher energy density, but the battery life you'll get out of most multi-rotors, unless you're building an extreme endurance one, is somewhere between 5 and 20 minutes. So the battery life out of this one, when I'm pushing it really hard, is between 3 and 5 minutes. Whereas the battery life out of the Inspire, it's much more efficient. You'll get about 20 minutes out of that, depending on how hard you're flying and what you're doing. The other value that you want to look at is your C rating, or your discharge rating. And that rating basically talks about how much current the battery can discharge without being damaged. So if you have a 10 amp hour battery and it is rated to 10 Cs, that means it can discharge 100 amps continuously without damaging it. Because 10 C means 10 times the capacity of the battery. So a 10C 1 amp hour battery cannot output the same amount of current as a 10C 10 amp hour battery, because that C rating is tied to the capacity of the battery. Have I confused you all with lots of terms yet, or are you all following along pretty well? Pretty good? Cool. And the fun things with LiPos is they explode. If you stab a LiPo or you crash into the ground with a LiPo, they will spew smoke everywhere and fire and hell and doom will happen. I'll tell you a funny story. I was building a hexa rotor at home, about 680 millimeters, and it had a 5 amp hour battery on the bottom, strapped to the bottom. I was using a Stanley knife to cut zip ties, and I accidentally slipped and went straight through the side of the battery in my bedroom, and it started spewing smoke everywhere, and I knew what had happened because I've watched lots of YouTube videos and I'm well aware of how big the flames can get. So I basically grabbed the discharge lid and thrown it out my window into the backyard, where it proceeded to spew smoke for the next 20 minutes and flames and other things. And that will happen, one, when you puncture it, but lithiums are also quite dangerous if you charge them too quickly. You put too much current into a battery. So most batteries you want to charge at 1C or 2C. So you only really want to charge it if it's a 5 amp hour battery at a maximum of 10 amps. But really you want to, that'll basically reduce the life of that battery, and you'll get less and less capacity if you do that. So you really want to be charging it at the capacity. So it's 5 amp hours, charge it at 5 amps, it'll take an hour to charge. If you happened to, say, plug a LiPo into a nickel metal hydride charger and give it 50 amps, it's just going to explode in your house. And that's really bad because you will burn your house down. So LiPos are something that you actually need to treat with a lot of care. A lot of people just sort of throw them around, but they are actually basically bombs. With laws and stuff, I won't talk too much about it because Mitch covered them mostly. But with airlines, when you're taking batteries on board, airlines basically, it's very vague. They say if the battery is under 100 watt hours, you're allowed to bring, so batteries first of all are not allowed to be checked in or stowed in your luggage that is checked in, not taken carry on, just not at all, flat out no.
If they're installed in your equipment.
If they're installed in your equipment, they're allowed. So you're allowed to, for example, put a laptop that has a lithium battery installed in it. You're allowed to put that in to check, but that's the only sort of a way you're allowed to get around that. If you're taking batteries on as checked luggage, if it's under 100 watt hours, you're allowed a reasonable amount, and that is the actual rule that they use. What a reasonable amount is hasn't really been proved in court before. But if you rock up with like 200 kilos of batteries, they'll probably start questioning. But in saying that, my friend Chad just went to Hawaii recently, and I think he took like 20 kilos of batteries with him, and they allowed him to do it. So
I took something like that to Norfolk.
yeah,
But, yeah.
you just got to be careful basically, because if they go off in the cabin, you're in for a lot of trouble. Over 100 watt hours. So for example, the battery in the Inspire one, this one here. There's two battery models in the Inspire one. There's the TB47 and the TB48. This is the 48. This is a 5,700 milliamp hour, and the 47 is a 4,700 milliamp hour. The 47 is 99.99 watt hours, which means you can take as many as you want. It was designed specifically for taking an aircraft. This one, which is slightly bigger, will give me an extra few minutes of flight time. Sorry. These, you're only allowed a maximum of 2 per person. So you're not allowed to take any more than 2 over 100 watt hour batteries with you on the plane. Now, whether you can just, hey, this person's with me, take 2 of my batteries, like that's theoretically okay. They may question it. You also have to cover the discharge points, so they can't just be like sort of bare exposed wires, because if you short batteries, they'll explode. And they have to be transported in a safe way. Again, it's very vague, but it's up to the person at the airport, basically. So that's batteries.
Can I just add on that?
Yeah,
Does
sure.
anybody understand why we don't check them in?
They catch on fire and then baggage underneath the airplane, nobody can do anything.
Exactly right. We can't actually get to your bags in flight, and if they catch fire, you've got no hope in hell. 2010, lithium polymer batteries brought down a DHL airliner and killed 2 pilots. In 2014,
It was last year.
the Air Fiji airline had a operator out of Melbourne taking drone batteries to Fiji, checked them in, didn't declare them, threw them in the bottom of the aeroplane. They caught fire before they even took off. They had smoke pouring out the side of the aeroplane. Don't check them in if you're going to take them anywhere, because you can't get at them when they catch on fire. It's not a matter of if, it's a matter of when. If you let these batteries get old enough, they'll just blow up.
And so what do you do if you can get to them? Immerse them in water, or is it?
No, the procedure for our flight attendants at the moment is to put them in an Atlas box and stow them at the right 2 compartment in the 20 or the aft back door. The main reason they do that is because the air in an aeroplane comes out of the air cycle machines and it gets pumped into various locations, primarily in the cockpit and then down the back of the aeroplane, and all of the air that is overflow, so to speak, goes down the outflow valve, which is out of the back of the aeroplane. If you put your smoky things down the back of the aeroplane, it gets sucked out of the back of the aeroplane rather than going all through all of the passengers. So they put them in one of the steel boxes, which is essentially what carries your food. Get it as far back in the aeroplane as you can, and all the smoke will get taken out of the back of the aeroplane.
And the thing with lithium batteries is the smoke that comes out of them is highly carcinogenic and very bad for you. Will give you cancer very, very quickly. Yeah.
Just while you're on the topic of batteries, can you mention how to dispose of LiPo cells that have failed and faulty, and also talk about the sparking risk? Because I think those are really important things.
Yeah, definitely. So if you do have a battery, for example, that is puffed or is looking pretty sad and you are kind of worried about it exploding, the best way to dispose of them that I've seen is basically put them in a salt bath. I'm not sure if that's how you do it. But basically you get a bucket of water, fill it with salt so that it becomes very conductive. And then you put, basically just leave the battery with the discharge points exposed in that water, and you'll have to leave it there for 24 to 48 hours. And that causes that battery to be completely discharged and removes any of that energy in there, so that they're not, basically they're not an issue. Then you can dispose of them in sort of like your battery world or whatever, and they'll take disposal there. Theoretically, you can throw it in your bin once you've left it in the salt water, but it's sort of not good to do.
Yeah, just to add to that, make sure you discharge the battery as much as you can before you do that. Because if you have a charged battery that you put in salt water and create a short, and all that energy starts to come out, and the water will start boiling off.
It's quite fun to
Cool to
watch.
see, but that's not good. And the other thing that you can do is if you have them discharged and put them in the bath, you perforate the cells with a sharp probe. That will ensure that any residual charge within the polymer lattice is actually allowed to discharge. I will ask you to put in proper battery disposal and not this into the general bin if it does contain metals and stuff like that. That's just not honestly.
Another way you can do it that I wouldn't recommend it is quite fun though, is you go to a big concrete area and get a knife and stab it right from the But that's quite dangerous and I'm not recommending it. But it's lots of fun. Yeah.
So apparently there's a safe storage voltage as opposed to fully
Yeah, sure.
about to fly.
Yeah, so with lipos as well, looking after your lipos, there's a bunch of stuff that you can do. So a cell, so each lipo, you're probably familiar with, lipo cells are 3.7 to 4.2 volts or thereabouts. And each cell, and then you connect them in series to get high voltage. So the battery in here is a 6-cell voltage battery, so it's 24 volts or thereabouts. Now, when you're fully charging your battery up to 4.2 volts per cell, if you leave it there without discharging it for an extended period of time, that will actually damage the cell and you'll get less life out of it after a certain amount of time. So it's good to discharge your cells down to about 3.7 volts, which is about 30% capacity, and that's sort of your storage voltage, and at there the degrading of the battery is very, very reduced. Now on the other end of that spectrum, lipos will also get damaged if you completely discharge them. They're not like nickel metal hydrides that have memory where you have to completely cycle them all the way to the bottom and then recharge them again, and sort of your lead acid batteries and those sorts of things. They're not like that at all, and if you completely discharge a lipo battery, you will kill it indefinitely. So you sort of want to be landing your batteries when you're down to about 3.5 to 3.7 volts. You don't want to discharge it any further than that, otherwise you will damage it and it won't recharge again, or it will explode in flight if you choose, or even when you're charging it. If you discharge it completely and recharge it, you'll have the risk of exploding it while charging. And also lipos, because they have a high discharge rating and they're high voltage, if you've got exposed wires and you touch them, they will spark and they will create big sparks. So whenever you're dealing with lipos, try not to have exposed wires. I have had a few times where I've done the stupid and you're changing the battery connector and it's got a positive and a negative wire and you're going, cool, I'll cut it off, and you get a pair of scissors, you cut through both of them at the same time and you short it through the scissors and you get an explosion in your hand. It's not fun, don't do it. So always be very careful not to have both battery leads exposed at the same time.
And on that topic as well, if you use lipo cells, particularly large acid lipo cells, don't wear a wedding ring, don't have dangling jewelry. I know a couple of people who lost their ring finger because they shorted the cross terminals and their finger went towards the corner off. So don't let it happen.
There's a lot of energy in these things, and if you short them, they will discharge their entire capacity in about like a minute. So, you're getting hundreds of amps through your finger. That's probably not going to be good for it.
And of course, when you're charging, you can put them in fireproof bags too. So if it does explode, you see the smoke and fire and flames and everything before it actually gets out of the destroy site, so you can manage it.
Yeah, a lot of people recommend actually just going to army surplus barracks and getting your ammo boxes, so your big metal ammo boxes. They're really, really good for charging batteries in. Those lipo-safe charge bags, there's a lot of really crappy clone ones out there that do not actually perform what they're supposed to. There's been a lot of people that have done tests on YouTube where they've exploded a battery inside one of them, the whole thing's caught fire and it hasn't done anything at all. So it's sort of like a false safety, so you leave it around and you'll actually burn the house down. Vessel blocks are also really good for charging in, so like your big concrete blocks, you leave them in the middle of that will do a good job of containing fire. And that's basically all I have to talk about batteries. Does anyone have any questions so far? No? Cool. So that's the basics of the normal parts of the quad. Now when you get into FPV, there are a couple of other parts that you put on. So you have the camera, you have the video transmitter, and the video antenna. And your frames will drop and you'll get compression artifacting and lots of other things. Whereas with analog, if you sort of get bad reception, you'll just lose a bit of static across it, but it's still seeable without any latency. Now with the Inspire 1, it's actually running a digital system, but it's got about 800 milliseconds of latency, which is not good enough to fly the proximity stuff that you do with these. Now there's two different types of sensors you can get on the cameras. There's CMOS and CCD. Most of them are all CMOS, which means that it does a rolling shutter, so it takes each line one at a time, rather than taking the whole frame at once, and then it just runs that through a loop. Now what that will cause is if your quad is not balanced and you're getting vibrations, you'll get what's called jello, or the rolling shutter effect, which is where the quad will have changed location while it's in the middle of capturing the frame. So you'll actually get little wobble lines through the frame that you're doing. Whereas CCD doesn't, but CCD is often quite expensive, and so most people just use CMOS and try not to have much vibration. You can also get cameras that are IR blocked or IR allowed. Basically, you can put a filter across your camera sensor that blocks the infrared light. So if you're flying during the day or flying in parks, that will give you a better color and a better looking signal that's not overblown. Whereas if you are trying to get a bit of a better picture at night time, you can get IR enabled, which is where it lets infrared light in, and you'll get a bit more sensitive to light at night time, but you'll lose your color. So you'll get some color, but it'll all be weird, and you'll get more sort of washed out looking color. Whereas on the Inspire 1, you've got a digital system, and it's digital the whole way, so it transmits the video signal from the camera it's a digital signal from the camera, then digital through the transmission into the remote, which then sends it out via the cable into the iPad. So you get a full HD. I get 720p video feed on there, which is really, really nice. It looks amazing and crisp. But like I was saying, the latency is not great, and if you do get lower reception, you'll actually start dropping frames. And to compensate for that, the Inspire 1 just increases the latency, so you sometimes get up to 2 seconds of latency, which is not good. On that note, you have antennas as well on your video transmitters. So these antennas, there's lots of different types of them. Originally, when people started doing these video transmissions, they were using what's called a linear polarized antenna, which is like this one here, where it's basically just a long rod and it transmits outwards. I'm not really a super RF guy, so I don't know the technicalities of it. But basically, if you have an RF, if you have an antenna like this and then you have another one pointed straight up, you're getting 100% signal. But if you're at 90 degrees to it, you're only getting sort of the cross-section of that, and you're losing a lot of the signal strength. On the other hand, you have what's called a circular polarized antenna. So I'll top off this antenna here. You can see it's in sort of a mushroom shape. And this one actually goes out in a circle, and it doesn't have the issues that you get with linear polarization, where whatever angle you're at, you don't lose nearly as much signal because of it. And there's a bunch of other types of antennas as well. So this one here is a directional antenna. So it has a 120 degree angle that it looks at or transmits at. So it's really, really bad sort of out here, but it's much stronger than an omnidirectional like this one that's pointing straight out. So for a quad system, you generally want to have like an omnidirectional on the quad, and then this is a diversity system where it has 2 antennas and it will swap between them. So I'll generally, when I'm flying, I will have one omnidirectional on here, so going all directions, and then if there's a rough spot like behind trees or something, you point your directional at that so you can get a bit better penetration with that. Now, the video transmitter itself is running on 5.8 gigahertz. Most people use 5.8. There's a couple of other systems that run on 2.4 gigahertz and 1.3 gigahertz for video. 5.8 is the only, 5.8 and 2.4 are the only bands that you can technically legally use in Australia without an amateur radio license, without being in other people's frequency. There's restrictions on the power that you can use, so the maximum power that you're legally allowed to use with a 5.8 is 25 milliwatts, and with 2.4 it's a little bit different. I'm not quite sure what it is, and you're not at all allowed to use 1.3 video unless you have a hand license, and I'm not sure what the power restriction is. If you do get your amateur license, you can take these up to 2 watts once you have your advanced amateur radio license. But then there's a lot of other things that you just need to be careful about, because there's a lot of stuff operating on the 5.8 gigahertz band. That's what a lot of your consumer electronics use. So you don't want to be like spewing signal across lots of things and taking them out. And so the thing with video as well, 5.8 gigahertz, is because the wavelength is so short, that means your antennas are small. So this one here is only a little one, so that's great for a mini quad. If you're using 1.3 gigahertz, that means that your antennas, generally like these mushroom ones, are actually about this round, and they're much more flimsy and easy to break, and they're a lot harder to put on a mini quad. The benefits of using low frequencies is because your wavelength is longer, it means that it can penetrate through objects better, and you get better range with it because of it. So 1.3 gigahertz will work much better behind trees compared to 5.8 gigahertz, and you'll get better range with it. But there are trade-offs that come with that. So that's sort of your video transmission. On the receiving side, you can receive it with one of these, and then it comes out of here, generally in like a composite video signal. And then that goes into your video goggles, like I have here. This one also has a receiver built in, but it doesn't have diversity, so it only has one antenna. So if I'm just sort of flying around me, I'll use this one, but if I'm going anywhere that's got sort of obstacles, I'll plug in my diversity. Now, these goggles, they have little screens in them. They're not like big, wide field of view. It's actually quite small. Imagine holding your credit card sort of this far away from your face. That's how big the video picture is. So a lot of people think you put these on, you're immersed in the image. It's not at all like that. It's not like an Oculus Rift. And that is actually a good thing. There has been a set of goggles come out recently called the head plays that have that wide field of view, and a lot of good pilots have actually flown around with them and find that there's actually too much information and it's a lot harder to fly than with these. So I actually prefer these. Now, legally wise, and I'll look to you as well on this, technically using the goggles is against CASA's regulations because you're not within line of sight because there is something impeding the vision. So there's a lot of push in the hobby industry at the moment, and a bunch of the people that I know are talking backwards and forwards with CASA about getting some more sane rules around FPV, allowing people to use it. But technically, as soon as you have these goggles on and you are the pilot, you are operating illegally. So I just had to get that out there.
There's a very funny situation there. It's completely illegal to do this FPV kind of stuff in Australia. The world champion is Australian.
He's a good mate of mine as well.
Yeah, definitely.
Is that even if you have a spotter?
Yes.
Yes.
Even if you have a spotter, that's the rules that we're looking at bringing in to allow people that have the other safety measures in place to allow FPV. But at the moment, you're technically operating beyond visual line of sight, like Mitch was talking about, and it's illegal.
And what would be the way to get around that?
Fly inside a building.
Indoors.
Because the rules don't apply when you're indoors and you need 4 walls and a roof.
Yeah, so there was a news article recently where Chad, the guy who won, was flying in a car park, and he was saying on that news article that that's legal because it's indoors. It's actually not, because the car park is not enclosed. There is not 4 walls, there's only a roof. So it's still technically illegal to fly in multi-rotas in car parks with goggles on. The other way to get around it is with something like a screen, where it's not actually impeding your vision between you and the quad, so it's completely legal for me to fly my Inspire 1 with the screen in front of me, as long as it's not like this. And as long as I can see the craft, that is where it becomes legal. Now, in saying that, people still do go and fly at parks, and I'm not going to say it's me at all, but with the goggles on. But technically you are operating illegally, and someone from CASA can potentially come and find you. It hasn't happened before, for many quads anyway, but it's just something that you have to keep in mind. I'm not going to condone it because I'm not the front, but come and talk to me afterwards.
If you have like one eye, I think like an Ardupilot system.
That is an interesting. So having the one eye is, I think, technically allowed. It's very hard to do. There are other ones. I have seen some people that have built FPV goggles that actually have a translucent screen, so you can, it's sort of like sunglasses where you put them on and you can still see the craft while seeing the video feed at the same time. I haven't personally used them before, but that's one way of getting around it as well. A lot of people who do it professionally that like the goggles have been trying out that model where they can actually see through the translucent screen, sort of like your Google Glass sort of thing. But yeah, so that's sort of your video transmission side of things. That's basically it for the video stuff. I've got this funny looking thing here. This is a I'll get to it in a second. This is an antenna tracker. So this has 3 what's called helical antennas. So they're extremely directional. They're sort of only 30 degrees because of the number of turns, but they're much more finely tuned for the area they're pointing at. Now this doesn't actually use all 3 of these for the video signal. What it does is it uses the video signal strength that's coming to each of these antennas to know where your quad is. So if it can see that it's stronger on this antenna and weaker on this one, it knows to rotate that direction, and it will actually autonomously keep the quad within the range of this middle antenna, so you get better video strength. These are much better suited to sort of your longer range FPV with like flying wings, because these antennas get confused when you're right next to them and you're transmitting power out. But it is a very, very interesting and useful system that you can potentially use if you have the license to operate outside of visual line of sight, like Mitch was talking about. What was your question?
You mentioned before you have your iPad set up on your controller. How common is it for people just to use their phone in coordination with FPV?
Okay, so for the analog FPV that you have on these, not common at all. And that's because there is not a good system out there for getting the analog video feed out of a receiver like this into your phone. There are a couple of USB on-the-go devices you can plug in that will get that video in, but the apps I've seen that people have got for that, they crash, they're quite unstable, and the latency is high because it's going into a digital system and it's doing analog to digital conversion. And I really don't feel like flying this when I think my phone might crash the app at some point when I'm 100 meters away. But there has been some people who've flown with phones before. They're much more common on your digital systems like the Inspire and the Phantom and those sorts of things. So that's it for the basics of the quad. How are you guys going for time? Like I can talk for another 8 hours if I want to. Are you guys like interested, engaged in what I'm talking about? Am I boring you? Can I get a bit of a thumbs up, thumbs down?
It's been good. But I've got a question for you.
Yeah, sure.
With the technicality, I'm interested on the computer vision side of things.
Yeah, sure.
Optical flow, is that just an example of computer vision, or is that different?
It's a very, very cut down, limited version of computer vision. So rather than it is computer vision. I could get a diagram up, but I didn't have time to prepare one. Basically, it looks at each pixel and uses computer vision to detect where it can see this edge moving to, and then calculates an average vector for that image, basically. So it looks to see, there's been a lot of stuff that I saw in the last frame that's moved down to the left by 3 pixels, therefore I moved that much. I don't know a whole heap about it, but it's very similar to optical mice. So if you'd call an optical mice computer vision, then yeah, sure. But it's very, very basic. It's not doing any sort of object recognition or surface recognition or anything like that. It's just looking at sort of the features that it can detect.
I know both, like DUT's really pushing ahead with that, so Professor Jonathan Robert wrote a paper on it with Peter Cork, but I know Peter Cork's the one pushing ahead with it. So looking, he's published some papers in Google whatever.
Yeah, Arca at QUT are doing a lot of work on computer vision that I've seen recently, as well as the Centre for Computer Vision Excellence at QUT as well. Okay, so flight controllers. There's lots of them out there. There's lots of them that do lots and lots of different things, ranging from a $15 KK board from Hobby King up to your $300 Pixel that you have in the APM system, all the way up to your $1,000 DJI proprietary system. It's just the flight controller for your A2 that you run on the big octocopters. There's a big spread of them. So there's a lot of different things to look at when you're looking at buying one. So initially, there was a flight control system called Multiweed. And if you look into it, a lot of older quads that were sort of on your hobby grade use what's called Multiweed. That's actually named after the Nintendo console. And that was because, if you guys ever remember, the Motion Plus adapter that came with, that you could buy for your Wii Remote, was one of the first cheap consumer available gyroscopes that was able to be purchased. At that point in time, 5 or 6 years ago, it wasn't actually that cheap to go out and buy a gyro that you could put on a quad. And Nintendo were one of the first people to do that in consumer electronics. So a lot of people were actually buying these Motion Pluses, looking at the I2C protocol, and they actually wrote a flight controller around this gyro that came with the Wii Remote. And so that's where Multiweed started. It was designed to work with Arduinos, so you saw your 8-bit processors pretty slow, so 8, 16 megahertz, that sort of thing. And that was sort of the norm for your small, cheap hobby multi-rotor at the time. There's also APM and Ardupilot. Also was originally designed for your Arduinos and your 8-bit 8-bit flight controllers. It has since moved up to 32-bit support as well, which is what the Pixhawk is. It runs at 200 megahertz rather than 16, so it's much quicker. You can have a look at one. The Pixhawk is quite an advanced flight controller. So you can see it's got lots of different ports, lots of different add-ons, and you can actually run a full real-time operating system on here with a Linux kernel and that sort of thing. And it actually runs the flight controller as an application rather than it being sort of bare metal, the only thing running on the flight controller. APM is really nice because it's got support for a lot of autonomous features like waypoints, on autonomous missions and that sort of thing. A friend of mine who works in the multi-rotor and the industry for that sort of stuff, he actually has his license and that sort of thing. One of his products that he builds is he has these fixed wings that he bought for $100 that look like an eagle, and he uses like Pixhawk or an APM in that, and has autonomous missions, and he sells it to farmers. And these eagle-looking things will actually circle around the crops to scare away any sort of pests and your crows and that sort of thing. And it can even the farmer just takes out this flying wing, puts it on the ground and hits go, takes up and it circles around the crops for half an hour and all the battery's going, and then it'll come landing again, he just swaps the battery and it goes up again. And he sells them for $2,000 or $3,000 to the farmers. But that's one of the things that you can do with APM. It's a really, really cool piece of kit. It's open source, so you can go on, that's the other thing, Multi-Wii is also open source, GPL license. So you can jump on GitHub and you can look at all the APM source code, you can contribute to it, you can look to see what pull requests other people are doing, and you can have a look into the code for that. On the complete opposite end of the spectrum, you have the flight controllers and the DJI systems. DJI is often thought of as the Apple of drones. They're very proprietary in what they do. Nothing is open source, nothing is modifiable. You buy it, you fly it, you break it, you send it back to it, sort of thing. You don't repair it yourself. So DJI are very much your proprietary, but they do what they do very well. The flight controllers in the DJIs are very stable. I was originally a DJI hater, similar to Apple haters, where you go, oh, I don't like them because they're expensive and they have this factor of people like feeling superior for having them. That all went away when I flew one for the first time. They're incredibly easy to fly and they're so stable and so nice. And that's why I own the Phantom and the Inspire one, because when I'm doing my aerial video work, I found that they are the easiest to use and they are the stablest. You can get quite stable with your APMs, but they require a lot more fiddling and setting up. You have to do a lot of tuning to get them working right, whereas the DJI sort of work out of the box and they're very, very stable like that.
We've launched an SDK as well now, so like it's almost as open as 3R is kind of going closed.
Yes.
And sort of super crossing over.
It's a little bit weird like that. So DJI have released an SDK. I have applied for and received access to that, so I can actually start writing stuff. I don't know how game I am to start writing like my own flight stuff on a $6,000 multi-rotor. I think I might stick to the pre-written stuff, but there's a lot of work going on by people who've written apps to do a lot of fun autonomous stuff. Like someone released an app for the Inspire One reason that does follow me, which is a feature that was generally only on the Phantom line. They didn't release that for the Inspire, but a third party released an app that allows you to basically have it follow your phone. It works quite well. So there is an SDK out there for that. Now, what do I run on one of these? So the racing quads, initially people ran Multi-Wii, but about 2 or 3 years ago, a guy by the name of Timecop came out with a board called the Nazi 32, running an STM32 board that was running at about 80 megahertz. And he basically forked Multi-Wii and made his own version of that called Baseflight. And Baseflight was designed from the roots of Multi-Wii to work on a 32-bit flight controller that was running much quicker. And that provided a whole avenue of basically increased performance that you could get out of these because they were able to respond to the changes of the environment much quicker. Now, if you've ever been involved with the multi-rotor community, there is a lot of, politics that goes around this. There was a guy by the name of Dominic Clifton who was doing a lot of contribution to Baseflight. And what he was doing, Timecop didn't like at all. he thought what he was doing was stupid. Even like he was adding support for other non-Nazi boards that were doing stuff, and he was adding support for RGB LEDs in it, so you can have like your indicator blinkers and like your little rev lights and that sort of thing. Time Cop thought that was completely stupid and revoked Dominic's access to coding in Baseflight. Even though it was GPL and open source, he said, "You're not allowed to do it. I don't want you to have anything to do with this." He wouldn't let him merge any coding. So because of that, Dominic started his own fork of Baseflight. Because it's open source, he can do what he wants. And he made a version called Cleanflight, which is called that because Dominic does a lot more work on trying to keep the code clean and maintainable. Timecop is a hardware designer, and because of that, his software is not super clean and easy to read. So Dominic has been trying to follow sort of the best practices with that, with unit tests and those sorts of things to make the code much easier to contribute to. So the Cleanflight is basically what everybody uses these days. Baseflight has sort of fallen out because everybody's gone, hey, this Timecop guy's a bit of a not nice person to deal with. And his fork of multi-lead Baseflight doesn't really get much contribution these days. There's not support for lots of different boards. It's basically died as a project. So there's Cleanflight. The other thing that Cleanflight added over Baseflight was a bunch of new PID controllers. Now, for you engineers in here, or those who don't know what that is, to stabilize these quads, they use what's called a PID controller, or a proportional integral derivative, which is a lot of fancy maths. It's basically calculus. And so if the quad if it's at this angle and it wants to be at this angle, it looks at what rotation it's doing and looks at the proportion, so how far there is between here and here where it needs to be. The integral, which is looking at basically how fast it has been moving, how far it has moved, the change in error, and then the derivative, which is the opposite. I always get them confused. It's a little bit of a confusing topic.
A derivative is rate.
Derivative is rate. What's the integral again?
It's the steady state error.
Steady state error, that's right. There's a lot of reading you can do on PID. I'm not going to claim to be a master of it. There's a lot of stuff you can do, an entire engineering degree around control systems. There's a lot of sort of PID tuning for dummies that you can do. But generally you'll have a PID loop running on your roll axis, your pitch axis, and your yaw axis, as well as your altitude and those sorts of things as well for stabilization. Easiest way to think about it is if you have an oven with a thermostat in it. If you say I want to get to 200 degrees Celsius, if you just leave the heating element running until it hits 200 and then say turn off now, the heating element is still hot, so it's actually going to go above 200. So it's all about tuning it so that it knows to bring down that heating element until it reaches 200. So there's a lot of tuning that goes into this. What I was saying was with Cleanflight, he actually brought in a bunch of new PID controllers that other people had written that did basically the stabilization slightly differently. One of them was known as PID Controller 2 called LuxFloat, which was actually starting to use the floating point operations that were available on the 32-bit controllers that weren't previously available on your 8-bit Arduinos that were mostly integer-based. So using the 32-bit controller, the new PID controller can actually take advantage of the floating point operations and be much more precise, basically. Now, there's another fork of Cleanflight, if that's not confusing enough, called Betaflight, that started about 2 or 3 months ago, that's right on the bleeding edge, that's done by a guy called Boris. And he's been doing a lot of work on just improving the performance that you get out of Cleanflight. So, for example, one of the things Boris has done is the gyro on here. Does anyone in here do any microcontroller programming and understand how that works for you guys? So if I say an interrupt, do you guys know what that is? So basically you have a gyro that's getting your data, that's retrieving it at, say, once every 1,000 microseconds. What it does is, traditionally on Cleanflight, you'd have what's called a loop time, where it does a loop of a set time, so 2,000 microseconds. And while it went through that loop, it would poll once every 2,000 microseconds and ask the gyro, what's your current value? What's your current value? What's your current value? And that meant that sometimes it was not quite getting the most recent data. Now, you've got to remember we're talking about microseconds here, so it's not a massive deal. But some of the stuff that Boris has been doing has actually been writing code that syncs that loop time up to the interrupts on the gyro. So the gyro says, hey, I've got new data. And then the flight controller goes, okay, cool, I'm going to start the loop now with that new data. Hey, I've got new data. And then it actually syncs that loop up with that. That's one of the things he's been doing. Another thing he added was a low pass filter on some of the PID stuff. So when we added in the ability to do your the floating point operations on PID 2, it actually started to get more unstable and harder to tune because there was a lot of vibration that it was picking up that it wasn't beforehand. Because when you're dealing with integers, it chops off everything past the sort of your points, your decimal values. And so when you start dealing with those floating points, you start getting all these little oscillations. So he's added filters in to sort of remove that while still keeping the benefits of your floating point. So that's sort of the state of the 32-bit hobby multi-rotors at the moment. There was another couple of projects, like one called Tail Labs and one called Ardupilot. They've had varying degrees of success. They're not really used. A couple of people might use them, but that's about it. There's been a bunch of changes also recently with the communication protocol between these receivers that go from my transmitter to my flight controller. Again, 5 or 6 years ago, that was all done via PWM, or pulse width modulation. So if you think of a square wave, where it's sort of like 50% duty cycle, on half the time, off half the time. So your value of your PWM was between 1,000 and 2,000 microseconds, and anywhere in between there's sort of represented the value. So when my throttle stick was at 0, there was 1,000 milliseconds was the length of that pulse, and when it was at full, it was at 2,000. And that was basically how it worked. So for each channel, you needed to have a wire. So you needed, for example, if I was running 6 channels, one for throttle, pitch, roll, and yaw, plus my flight mode and my arms, for example, you needed to have 6 wires running from your receiver into your flight controller. Now that's not good. So they introduced something called PPM, or CPPM, which is Combined Pulse Position Modulation, which basically combines all of them down into one wire. So that allows you to communicate from your receiver via one wire and send all up to 8 channels via one wire rather than having to run 8. And that's what people have been using for a long time, like a year or two now, and that's sort of been the norm. But there has recently been a push to move from that, which is actually an analog system, because it's sort of reading it between 1,000 and 2,000. There's a bit of jitter. There's been a lot of push to move to digital-based systems, because with the analog system, when you're running PPM, there's actually a bit of latency. Because it's combining all 8 channels down one wire, you're actually getting, I think we calculated it recently, up to about 80 or 90 milliseconds between when you move your stick and when it actually moves the quad. Because it was analog, they were running an average across those values to get any jitter out and all those sorts of things. So there's been a lot of people moving to what's called S-Bus, which is a completely digital system, which has 9 milliseconds of latency and doesn't have that jitter. But that's something that's only sort of been happening in sort of the last 4 or 5 weeks inside the multi-rig. Very, very bleeding edge. The other change that's been happening is the communication between the flight controller and the ESCs themselves. So these ESCs, these are sort of the premium ESCs on the market. It's called KISS ESCs, or Keep It Super Simple. They're quite expensive. These are by a German guy called Felix. The nice thing about these ESCs is they were the first ESCs really to do braking, where they will actually, if I bring my throttle down, rather than just let the motors freewheel, if I bring my throttle down, it will actually actively brake that motor so that it can drop quicker. Normally when you punch out and bring your throttle down, it would balloon up and slowly come back down again, whereas now you get much more response on your up and down axis as well. The other nice thing that this specific ESC does is it will actually do regenerative braking, where it will it'll take that energy that it's gaining from slowing the motor down and redistribute that back up the wire to the other motors, or if it's not going anywhere else, into the battery again, so you get slightly better battery life. The merits of that have been disputed a lot by a lot of people. It does actually work, but it's sort of like a 5% difference. Since then, there have been a lot of other ESCs on the market that have started to introduce this braking, but the FETs on here are much higher quality, which is why you pay $40 or $50 per ESC rather than 10. Now, firmware on the ESCs is something that has, up until last year, pretty much stayed the same. But there has been a big push recently, and there's a lot of new firmwares coming out for these speed controllers to increase the refresh rate that these are having. So a year ago, most speed controllers were running at 50 Hertz, where they were changing the speed of the motors 50 times per second. That's actually been boosted quite recently by a protocol change to what's called one-shot, where the flight controller, rather than sending on, its continuous 50 times per second, it just sends this data that it's got now. It actually syncs the data that it's sending to the ESCs with when it has new data. So when it has new gyro data, it sends it straight away to the ESC, which means it can be up.
Has recognised that and said, look, there is parts that are good and there is parts that are bad. And what they've done is they basically put the burden on the operator and say, you need to make sure it's safe. They don't care how you do it, they just say you need to make sure it's safe. And that's why they appoint the position of a maintenance controller in a company. And if the maintenance controller considers it safe and it turns out to not be safe, it's not CASA's problem, it's their problem. They've got to sort it out and they become liable. And that's why insurance is a big thing at the moment. If you're flying one of these things around commercially and you don't have at least third-party insurance, you're stupid.
You want to have sort of at least $10 million public liability.
It's just comes down to these components. I've had the weirdest things fail on me that you just wouldn't think would fail. And then 5 seconds later you go and hit a bird and everything fails. And you're kind of like, well, I didn't exactly account for that. So, yeah, CASA approaches that with the mentality of it's your responsibility to make sure it works like that. The other problem that they've got at the moment down in Melbourne, the guys down there had a problem where the ATSB put it down to, the ATSB is the air transport, aviation. Yeah, the guys who investigate crashes. They had an accident down there with a rather large helicopter flying overhead, like the MCG kind of area, and it ended up crashing.
Was this a multi-rotor?
Yeah, it was a multi-rotor. Yeah, it ended up crashing. They released a report about 4 weeks ago. And they put it down to the fact that there was 100,000 people in the MCG and the mobile phones probably stuffed it up. Probably a pretty good reason, but it's still a very contentious issue as to whether that can interfere with the multi-rotor. So CASA's now put not a restriction, but a burden on the operator to prove to CASA, before completing an operation like that the EMF will not interfere with the UAV. And nobody's really figured out a method to do that. All of my operations that I used to do for a lot of the stuff down there, overhead the Wallabies games and stuff like that, it's all stopped because we don't know what mobile phones do. Yet I've done it about 50 or 60 times and it never did anything, but now all of a sudden it's stopped. It's all reactive rather than proactive approach in this industry, unfortunately. So.
And just on what Mitch was saying about when you have someone who has an operator certificate or business, they have a maintenance person. You'll have to have a maintenance schedule for the class for the crafts that you're flying. So, for example, with the Inspire 1, it's recommended to replace the motors after 100 hours of flight, just because it is a mechanical system and mechanical systems do fail. You're supposed to replace your propellers after a number amount of flight hours. You're supposed to replace your motors. Most things have a limited life. For safety, that you're supposed to sort of replace them, not fly them until it crashes. And that's something that is, again, your burden of proof that you as the maintenance officer has to research and go, I think that the motors will probably last about 100 or 150 hours, so I'm going to replace them at 100 hours. And that's up to you as a business to come up with those figures.
So that UAV companies will go through a whole process of taking all the components of their aircraft and testing them to failure. Not just one, but actually test 10, sometimes a dozen. Either, depending on what the component is and how critical it is, to find out how long they'll last until they'll fail. From that, they'll do statistical analysis and work out what their acceptable failure rate will be given a certain operating time for that component. Like I said, if we told just put a whole bunch of servos on a torsion test and just ran them until they failed, and they came up with a statistical model for the servos with guys and replace that part. And just on the point about redundant systems, it's actually possible to make a quad rotor that loses a rotor by going into a flat spin, so that it evens out the uneven vector of the remaining 3 rotors. So you can actually set down a quad even without redundancy.
It is theoretically possible. I've seen it done as well. The guy in the TED talk actually takes 2 of the rotors out on his multi-rotor and then he has 2 left, and it just spins uncontrollably. The problem with that in most consumer systems and ones that you will build yourself is getting that feedback from the motor so that it knows that this motor has gone out. is something that most consumer products don't do right now. There's no way for the motor to report back to the flight controller that, hey, I failed. And so it's theoretic. It was in that TED talk. It was possible because it was a controlled environment that he had modelled in a system where it had been tracked, sort of with external cameras, and he knew everything about that. And he was able to say, hey, these 2 motors have failed. I'm telling you that. Now act like that. It's hard for something like an Inspire 1, if, for example, my propeller flies off, for it to tell the flight controller, hey, the propeller's flown off, please land safely, because it doesn't actually know that. It just goes, hey, I haven't got enough thrust on this motor, give it more. And there are some people that are doing research into that, but it's not currently in the consumer market anyway.
I guess that's what the D and the PID accounts for. If you got some sort of acceleration or rate, increasing error, that's accelerating.
Is it like detecting the current usage, or how they change that, or whether they've got
the way that they actually detect it in motors is using, I think, Hall effect sensors, where they're actually like measuring the rotation of the motor. These ESCs here actually have a basic. So generally, to detect whether a motor has stopped, you actually need more than just the 3 phases. You need another sensor in there to detect that. These ESCs actually are super clever and are able to, with some level of certainty, determine whether the motor is working or not based on the phases and the power that is pulling on each phase. And that's useful in this case not to allow it to land safely, but if you have a propeller that is blocked and it's telling the motor, go at 80%, but I'm holding the motor, you will overwork the ESC and it'll catch fire. I've seen that happen before. I've done it myself at ESCs where they get caught in the grass and it's trying to spin the motor, but it can't, and the ESC just goes above its amp rating and blows up. So these ESCs have a really nice feature in them where they will sort of try and guess whether the motor is stopped or not, to be able to basically cut it so that it doesn't blow itself up. Cool. Any other questions? Yeah.
Like back to on the previous point,
sure.
About maintenance officers or controllers or whatever it was. Does that mean if Robotics has to get a license if they become quantum secure? Does that mean we also have to designate like all this kind of control that they do in ordinary aircraft carriers? So you need a maintenance control, you need someone to take care of the districts and stuff.
Yep.
You have to build up all those levels.
So when you apply for your operator certificate, you actually have to write in your paperwork who in your business is the designated maintenance officer and what was the other one?
Chief Controller.
Chief Controller.
The ruling says you must have a company structure that provides for the safe outcome of the operation. So if you're a company that's one person, that's pretty simple. If you're a company like the university, you're going to have quite a large database of people who have pilot's licenses or certificates. So you need to have a company structure that's suitable for that. In my operation, I used to be the chief controller and the maintenance controller. That got a bit too out of hand for me to do both jobs, so now I've separated that. Somebody else is the maintenance controller. CASA then turned around and said, oh, well, you can't do all the chief controller work yourself, so we now have a compliance manager, and we also have a chief flight instructor as well now. So depending on what the company is doing, you need to formulate a structure, and then they will approve that, or I don't think the correct word is probably approve it. They will approve that as a part of the operations manual suite, and then you effectively are required to operate in accordance with the operations manual.
Yeah. The other thing that, sorry, you go.
Did CASA like specifically tell like your company or whatever that you must have this many people for, like if you have one chief controller for a company of 5 people, is there like a limitation? Is there a set?
No, there's no strict limitation. CASA's the way the laws are written, CASA can pretty much say whatever they want. As much as in CASA's opinion, if they deem something to be in the interest of safety, they can pretty much say, we're doing that. They came to me and said, if you've got about 15 aeroplanes, you'll be fine to do it by yourself. And then when we started getting to about 35 and 40 with about 25 odd staff, they started saying, all right, well, how are we managing this? What's happening here? So we started an internet-based management software program all through our internet. And then that kind of developed into separate out the positions. Everyone's got their own job description, title, and their own requirements or reporting factors to CASA. And then once a year we have or once every 3 years we have an audit, and CASA essentially can log into our intranet, which they do quite often, and just see what's going on. And we kind of keep it all that way for them. And that way the workload on me gets reduced and everything's spread out, so there's less likely for mistakes, errors, things like that.
The other thing that I forgot to mention, when you're applying for your operator certificate, is you have to provide, because you apply for it for a specific type of craft, you have to provide the manufacturer's paperwork for that. So if you're the person who built your own, so did you build this one yourself from parts? You will actually have to, if you want to fly this commercially, come up with your own, probably 100-page document documenting every single part on there. And all of
pages, but yeah.
Sorry?
It was about 35 pages.
Sorry, 35. It's a lot. It's a bit of paperwork that you have to do, basically, that says what all of the shearing points of the bolts are and everything. Like, you have to document everything about that craft and what it's rated to. The nice thing about having an off-the-shelf product like an Inspire 1 is I can say, use the pre-made one that DJI made for me. So I originally was going to be doing my operator certificate with a hexa rotor that I built myself on a frame that I built from the hobby store that has 6 propellers, retractable landing gear and all that sort of stuff. And I looked at the amount of paperwork I'd have to do and work out all that sort of stuff, and I figured it would actually be easier for me to buy one that already had that paperwork done for me, which is why I'm running the Inspire 1. Cool. Yeah. And the other thing is with the Inspire, I can have a little bit more peace of mind and I don't go, well, maybe that solder job that I did wasn't quite up to scratch, maybe it's going to fail or something. I know that this is a commercial piece of kit rather than, hey, maybe this wire I put in had a break in there that I didn't realize or something. Then it's sort of a problem that I could have created, whereas this is much more, I guess, peace of mind using one of these pieces of kit. But that's up to me. That's just my personal opinion.